Hello, everybody. This lecture is the second one about gravitation. So the first lecture I talked about Newton's universal law of gravitation, which gives you the force between two masses. In this lecture, I want to talk about the energy, in particular the potential energy due to the gravity of the Earth, due to the force of Newton's universal law of gravitation. So uh, again, first of all, we got to remember a lot of stuff from Physics 221. And so I'm going to start out by kind of reminding you of some of that. So we're talking again about gravitational potential energy. Now, if you remember from Physics 221, we're going to use the letter W for work, and U represents the potential energy. So in Physics 221, we found that potential energy near the Earth due to gravity was mgy, or sometimes people use mgh. And the potential energy due to a spring, for example, was 1/2 kx squared. Now, how did we get the potential energy, and how is it related to the work? So if you remember, the work is defined to be basically the force times the distance. So if you do have a variable force, for example, the spring, it depended on x, you've got to actually do an integral of the force over that displacement of the spring from its initial displacement or initial position to its final position. Now, since we're talking about Newton's law of gravitation, our variable is r here, right? The distance between the masses. And so we're going to end up doing an integral from r initial to r final over that force. And if you remember from Physics 221, for these forces, which we call conservative forces, you can define a potential energy. It's related to the work by the fact that the work is the negative of the change in the potential energy, U final minus U initial. All right, so let's go ahead and use this to calculate or try to determine what the potential energy is for the force between two masses here. And the way we usually think of this is we've got one mass, a large mass, like maybe the mass of the Earth, m1, and a smaller mass out at a position r, right? And sometimes people would call this a test mass. And we're kind of talking about this test mass, which might be like a satellite moving near the Earth. It's moving in that source mass or that larger mass's gravitational field, so to speak. Now this r hat over here just reminds me that I'm saying that r is positive going outward from mass 1, right? And that has important effect on the work, right? Since the force is actually attractive, it's pointing in the direction of negative r. And so if I try to move this mass outward, the work done by the gravity, the attraction to m1, will actually be negative, right? Because you're actually going opposite the way that the force is acting. Your displacement and your force are in opposite directions. So if I try to calculate the work, I need to remember that my force that I'm using is our Newton's law of universal gravitation. Right? Negative because it's attractive. Again, it's in the negative r hat direction. G m1 times m2 over r squared. So that was from our first lecture. That's our Newton's law of gravitation. And so when I plug this force up here into my definition of work, I basically get this integral, right? And I'm going from r initial to r final. Now, I'm not going to go through the detailed steps of doing the integral, but what you can do, the g, the m1, and the m2 are constants. So they just come out along with the negative sign. And I get the integral of 1 over r squared dr. Now the integral of 1 over r squared is negative 1 over r, right? And so basically what you end up getting when you plug in the limits is that the work is equal to gm1 m2 over r final minus gm1 over m2 times r initial. So I've calculated the work. I want to identify what the potential energy is now. And I'm going to just pull out a negative sign to do that so that I can get it in this form, right? I want it in this form. So I pull out my negative sign, so I get this expression. And hopefully you can see, right, I've basically got my U final minus my U initial. And so what I can do is identify that my potential energy due to gravity is negative G M1 over M2, or M1 times M2 over R, the distance between them. Now, you might wonder how this is related to MGY, right, when you're near the surface of the Earth. It turns out you can prove that this reduces to that, but I'm not going to do that right now. I guess if people are interested, I could do a video or a discussion about that. But what I want to do now is kind of remind you of some stuff that we do in Physics 221, which is that we use the conservation of energy. And I'm going to use conservation of energy to calculate what's called the escape velocity for the Earth. So say you had a rocket at the surface of the Earth and you wanted to shoot it so it could get infinitely far away, right? It can make it actually out of the Earth's gravity, so to speak. What speed, what initial speed would that rocket have to start with to do that? So we're going to look at how do I calculate escape velocity. So the escape velocity, again, I've got my rocket here. Sorry. I've got my rocket here at the surface of the Earth, radius of the Earth, the mass of the Earth, and I want to remember that anytime I'm outside this sphere, I can treat the mass of the Earth as if it were at the center, right? So basically my R initial is RE, my R final, when the rocket gets infinitely far away from the Earth, is infinity. And I'm going to use our old conservation of energy, right? I'm going to start with some kinetic energy, maybe some potential, but the total kinetic plus potential energy must equal the total final kinetic plus potential energy, right? Unless you had friction, which we dealt with, but there's no friction here, no atmosphere. We're out in outer space once we get away from the Earth. So let's fill those in. So my initial kinetic energy, right, is my 1/2 mvi squared. My initial potential energy is negative gm1 m2 over ri. I've got the same sort of expressions for the final values. And when I plug in my R initial and R final and everything, I do have my initial kinetic energy. My VI is going to be my escape velocity, but my initial potential energy is actually negative, right? Negative GME times M, my mass, or the rocket's mass, over RE. Now the final kinetic energy is 0 because I want to just barely escape. I want to end up infinitely far away with just 0 velocity. I'm just barely going to get out of the Earth's orbit. My final potential energy is 0 because R final becomes infinite, right? It's huge, making this basically 0. This might look a little strange, but this is often what happens when I'm stuck to the Earth, right? I've got to have enough kinetic energy to sort of get out of this potential hole, this negative potential energy that I have. So if I just rearrange this, I see that 1/2 mvi squared equals GME m over RE. So basically what has happened is I've transferred that negative potential energy into kinetic energy. And I can then solve for my initial velocity, which is my escape velocity, right? And I get this expression, right? Just canceling out the rocket's mass. It doesn't depend on the mass of the rocket, as it turns out. So I just did some algebra to solve that, and that is my expression for escape velocity. Now, if you wanted, you could plug in your values for the numbers here, the G that we talked about in the first lecture, that gravitational constant, universal constant. Mass of the Earth is this, 5.97 times 10 to the 24 kilograms. The radius of the Earth turns out to be 6.38 times 10 to the 6. And so if you plug these in and calculate your escape velocity, you get about 11,200 meters per second. Converting that into miles per hour, you get about 25,000 miles per hour. So you have to have that speed when you leave the Earth to actually get infinitely far away, just barely, right, with 0 final kinetic energy. So just reminding you again, one of the main things here is that my expression for the potential energy looks like this. This lecture is in a way sort of optional because I'm not going to ask about this, but we will see an exactly similar expression when we talk about the electrostatic force. It turns out all the math is very similar. So you won't see really questions about this on the reading quiz for this stuff, but I think it's a good review. It'll also make a good connection with electric potential energy when we get to that point. So for that, I'll leave you until the next lecture. Thank you.